Hello, how are you? I'm Ryan. Welcome back. It's day 10. Yesterday, we got wrecked at Avenue Code. It was like a 2 hour video. I wanted to cry. It was fine. I didn't cry. Instead, I came back the next day to kick some coding puzzle butt. For those of you who aren't familiar with the series, every day for every day of December, there's two coding puzzles that get unlocked on like a 24-hour interval, and about 21 minutes ago, day 10's puzzle came out. So it is December 9th for me. It's December 10th if you're on the East Coast. And we are just gonna, I don't actually need these. We're just gonna dive in, and we've been solving all these puzzles in a language called Elm that compiles the HTML. So I have the Elm source code on the left, and then I've got a little HTML viewer on the right. So as we go, we're gonna just be kind of going step through step through the problems, how I solved them, and then I'm going to be posting the solutions in the video description below, as well as links to Ellie, which is kind of our code pen for Elm, and Advent of Code, so you can sign in and try the puzzle yourself. But that's my intro. Let's dive into day 10, and let's make sure to read the instructions very carefully, because not doing so cost me about 90 minutes of my life yesterday. So, day 10. All right. Cathode ray tube. You avoid the ropes, plunge into the river, and swim to shore. The elves yell something about meeting back up with them upriver, but the river is too loud to tell exactly what they're saying. So we're like elves trying to go through a jungle or something. There's a bunch of lore that you might have missed out on. Anyway, they finish crossing the bridge and disappear from view. Situations like this must be why the elves prioritize getting the communication system on your handheld device working. You pull it out of your pack, but the amount of water slowly draining from a big crack in its screen tells you it probably won't be of much immediate use. Unless that is, you can design a replacement for the device's video system. It seems to be some kind of cathode ray tube screen and simple CPU that are both driven. Oh gosh, I just saw a glimpse of the ADX. We're making assembly again. That are both driven by a precise clock circuit. The clock circuit ticks at a constant rate. Each tick is called a cycle. Start by figuring out the signal being sent by the CPU. The CPU has a single register, X, which starts the value 1. It supports only 2 instructions. Add XV takes 2 cycles to complete. After 2 cycles, the X register is increased by the value V. V can be negative. A no-op takes 1 cycle to complete. It has no other effect. The CPU uses these instructions in a program, your puzzle input, to somehow tell the screen what to draw. Consider the following small program. We get no-op, add x3, and then add x negative 5. Execution of this program proceeds as follows. At the start of the first cycle, the no-op instruction begins execution. During the first cycle, x is 1. After the first cycle, the no-op instruction finishes execution, doing nothing. At the start of the second cycle, the add x3 instruction begins execution. During the second cycle, x is still 1. During the third cycle, x is still 1, and after the third cycle, the add x3 instruction finishes execution, setting x to 4. At the start of the fourth cycle, add x minus 5 instruction begins execution. During the fourth cycle, x is still 4. During the fifth cycle, x is still 4. After the fifth cycle, the add x minus 5 instruction finishes execution, setting x to negative 1. So it goes from 1 to 4 to negative 1 because you subtract 5. Maybe you can learn something by looking at the value of the X register throughout execution. For now, consider the signal strength, the cycle number, multiplied by the value of the X register during the 20th cycle and every 40 cycles after that. That is, during the 20th, 60th, 100th, 140th, 180th, and 220th cycles. Every 40 cycles after that. Okay, so this is a larger program. That is a larger program. Oh my gosh. The interesting signal strengths can be determined as follows. During the 20th cycle, register X has the value 21, so the signal strength is 20 times 21, which is 420. The 20th cycle occurs in the middle of the second add X, so the value of the register X is the starting value. 1 plus all the other add X values up to that point. Cool. During the 60th cycle, register X has the value 19. So 60 times 19 is that. 100 times 18 is, okay. So we're taking register X, we're multiplying it by the cycle. and then we're adding all those things up. So when we add up 420 plus 1140 plus 1800 plus 2940 plus 2880 plus 3960, we're going to get this. So the puzzle is asking us to find the signal strength during all those cycles. What is the sum of these 6 signal strengths? So we're going to keep going 6 times. We'll see how that goes. So what I want to do is I want to start by taking this little puzzle input here and just make sure that we are running our program correctly, just at a very basic level. So this is a little kind of program setup that we have. We just take the string, we wrap it in quotes, and then we print it out to the right. So that's what you're seeing here. The first step I want to do is I want to break apart each instruction by line here. So now for each instruction, we have a list of strings, and for each instruction, it's just going to be a string. So what we're going to do is we are going to use filter map to turn this into a specific instruction. So it's possible that we are able to understand the input, and it's also possible that there's something wrong. So what we're going to do is we're going to define a custom instruction type. It's either no-op or it's add. And then I guess addx is what I'll call it. And then addx will always have an integer to keep track of. Addx will always keep track of like how much it's adding. There's probably some additional information that we might need to keep track of, like how many cycles are left, something like that. But I'm not going to worry about that too much. For now, this is us just taking the strings and turning it into some structured data that we can perform some logic on. So most Elm programs will kind of start by doing that. So we're going to do string.words. That's going to split our string by spaces. We could also use split space. String.split, string.lines, and string.trim. These are all built into the core Elm library. So we're taking advantage of that. And then what we're doing is something called pattern matching. So if we split these strings up, and we get just no-op, what we want to do is say, yep, let's successfully return no-op. If we get addx and then some number string, so like some text that follows after, what we want to do is say, in the case where we can successfully turn this into an integer, that's great. So if we get the integer, what we want to do is say add x. I'm going to use a capital X because I think that's what I'll type more frequently. I don't want to accidentally be typing the wrong thing. But if for whatever reason we get addx and then a non-number value like addx banana, we're just going to say that's invalid input and we're going to ignore it. So every branch of this where we return nothing, we're saying just ignore this instruction. We don't want to keep it. So hopefully when I hit compile, what we'll see is we'll have, instead of just these raw strings, we're going to get a list of instructions here. Great. So this custom type basically says instruction will either be no-op or it'll be addx. If it's addx, it's going to hold on to an integer value. So what you're seeing here is that these are kind of getting parsed into these nice types that we can work with. So we can use this instruction to figure out how we want to change the program. So what I'm going to do is I'm going to do something that we've done in the past where we've used a fold-L and a function called perform instruction. And we've initialized a model. And what we do is we basically keep looping through all the instructions and keep cycling until we're done running the whole program. So what's this model, what's this init, and what's this perform instruction thing I'm talking about? Let's define the state of our little computer. So our computer has a cycle, which is going to be like the integer, basically the clock. And then we'll basically we'll start the program on cycle 1. And then what we want to do is we want to have a value for register x, which is initially also going to have a value. And then I think what we want to do is have some number to represent like a countdown for are we ready or not. We're going to need something in our program to basically say am I busy running an instruction or not. So I'm going to say status, and we're going to use a custom type for this. So status is either going to be ready or running for int. So the int will represent how many cycles that we're running for. So what I want to do is I want to say when our computer starts up, we need to define what its initial state is. That's what the init function is going to do. Init is going to say, I've got a cycle, and initially I think the cycle is just 1. Maybe it starts at 0. At the start of the first cycle, the no-op instruction begins execution. During the first cycle, x is 1. After the first cycle, no-op finishes doing nothing. So I think we do want to start the clock at 1. And then register x is going to have a value of, during the first cycle, x is 1. And then finally, our status is going to be ready. So when we perform an instruction, what we need to do is we need to take an instruction. We need to take in our current model and return our new model. And we're going to use this status to determine if we're going to run another instruction or if we're going to kind of tick down. So running int, I'm also going to keep the instruction here. So either we're ready to run something, or we're running an instruction that takes a certain amount of time to run. So what I want to do is I want to say our input is instruction and the current model. In the case where our model.status is ready, what we're going to do is we're going to perform the next instruction. So we're going to case off of the instruction that we get. I'm going to say execute instruction model. We'll define that function together in a bit. But if I'm running an instruction, this is going to be instruction. I'm going to call this, just to avoid confusion, I'm going to call this the next instruction. So I'm going to be running the current instruction. I'm going to have a counter. And what I want to do is I want to decrement the counter here. So we're going to say if counter -1 is 0, then we are going to we're actually gonna execute. We're gonna actually do whatever the instruction is. So finish running instruction. Maybe this is gonna be like start instruction. I'm gonna call this start instruction. I'm gonna call this update. This is kind of like a thing you'll see in most Elm programs is update and init. So this might look familiar to you if you've made programs with Elm before. There's always an init and an update function. So start instruction, next instruction model. Okay, so we're gonna figure that out. And then else we are going to set our model so that the status equals running current instruction. And then I don't like this actually. I don't like how this is shaping up. So let's just let's ignore status for a second. Let's see if there's an easier way to do this. So what I'm going to do is we're just going to match on the instruction. I'm going to start simple. So each instruction has a certain amount of steps. So no-op will two entries, I guess. I think I want to collect a history. Okay. Well, let's just focus on getting the program to return the right value, and then we'll worry about kind of making it perfect. So what I want to do is when no-op happens, all I want to do is take the cycle and basically just add 1 to it. and then return. And then if I have add, what we're going to do is we're going to have the amount that we want to add. How this is going to work is it's going to take the cycle. Like a simple implementation would just update it by 2, and then the amount we want to add is going to be register x equals model dot register x. The current value plus the amount that we're going for. So if I run this, at the end we have our cycle is 6 and our register is at -1. After the 5th cycle, yeah. So yeah, setting x to -1. So after the 5th cycle, we get -1. So that sets our kind of clock to 6. What I want to do is I want to say that I want to kind of log the values at 20, at, what is it, 20, 60, 100, 140, 180, and 220. So what I want to do is there's going to be like the new model and the old model. So I think what I'm going to do is just make a quick let expression, say new model. So model, this is what we're kind of returning right now. But I want to do a bit of logic here. So right now we can just return this and we'll get the same answer from before. So we still get cycle 6 and register -1. So I'm going to say we're going to take the range of numbers, like the cycles that we went through, and I'm just going to show you what that looks like. So cycles is going to be a list of ints, and it's going to range from the cycle that we were on when the thing started all the way to kind of like the new model cycle. So for each instruction, I'm just going to kind of print this here. What you're going to see is a list of integers get printed for every command that we run. So I think what you'll see is that 1 was happening when we had the no-op command. So I could also do a debug.toString just to show you the instruction that ran. And so you'll see in the header here, when the no-op command ran, it was going over 1. When the addx3 command ran, it was going over 3. addx-5 command ran, it was going over cycles 4 and 5. What I want to do is I want to check to see if any of these numbers kind of matches those values that we care about recording, and if so, I want to insert into like almost like a history like lookup, so we can say, hey, what was the value at 20? What was the value at 60? What was the value at all these numbers? So 20, 60, 100, 140, 180, 220. So what I'm going to do is I'm going to say that the values that we care about, this is the dumb way to do it, which is just like to list the values. 60, do this, 100, 140, 180, 220. We could have code that generates this, but we're just going to add 40 to this all the way up to 220, I believe was the last one. So these are the values that we care about. So cycles to record, oops. So these are the cycles we want to record. This is going to be our history, which is going to be a dictionary that if you give me a cycle, I guess I could start making some aliases for this. I'm going to give you the register value. So we can call these register values if you want. You can call these cycles. Elm's got this really cool feature with these type aliases where you can help make your code more readable by just making nicknames for types that, even though they're the same value, just make the code a little bit easier to understand, and makes it easier for me to talk about kind of what's the key and what's the value for the dictionary. So a dictionary is a built-in data structure. Format this. So this is an int. That's good. This is a cycle. This is a register value. This is a list of cycles. And I think that's pretty good in terms of annotations. What I want to do is ask, or I'm just want to, I'm going to have whatever the new model is, but I'm going to record, update the history for these cycles. So what I'm going to do is I'm going to pass in the cycles that were hit for this. So these are the cycles that this instruction ran for. I'm going to have the before model and the after, which is our new model. And hopefully this will kind of append information that we need to do our calculation. So update history for cycles is going to take in a record with a cycles field, which is a list of cycles. So we're going to pass that in. We're also going to pass in the model that we had before. We can also make this like the register value, I guess. Register X, register X here. So maybe we'll just only worry about this, register X. After X. And then let's just pass in the full model. The reason I'm going to do that is because we want to return the new model. This is going to be the before. This is going to be the after. These are all going to be models. And what we're going to do is we're going to return the dictionary here. Okay, so that was kind of a lot, but what we're trying to do is we are taking in our cycles, taking in our before and our after state. And what we want to do is we want to loop through all the cycles that we hit, filter to the ones that are included in the ones we care about. So if they are a member of cycles to record, we'll keep them around. So let's do that piece by piece. We'll take the cycles. We'll filter each cycle. So for each cycle that we ran. So the first time it comes in, it'll be 1. The second time it'll be 2, 3. The third time it'll be 4 and 5. We're going to ask, is this cycle one of the ones that we care about? So is that cycle in the list cycles to record? If so, what we want to do is we want to turn this, I guess what we want to do is take that cycle and we want to record the register value before, because remember how -5 runs at the end? What we want to do is for that cycle, we want to return that cycle and we want to return the register value before. So before.register X. This is going to return us a cycle and a register value. We can turn that into a dictionary by using dictionary from list. And then what we can do is we can use, there's a dictionary.merge key, dictionary.add or something. But what we want to do is we kind of want to combine this dictionary with another one. So union. Preference is given to the first dictionary in that case. So I don't think we'll have any issues with that. But what we're going to do is we're going to combine that with our existing kind of collection of history we have. So cycle number register X. We see 57 and 58. Oh, right here we need to initialize the dictionary. So initially we don't have any information. We don't have any history. Okay, this is good. Let me just annotate really quickly kind of what each of these types are as we go, so you have a little bit of an intuition for what each step is doing. So cycles, when it comes in as a list of cycles. When we call this .filter, we're not changing the type, we're just taking things out of the set. So every time I write a lambda in Elm, I always think it's better to say like, we should make a named function for it. So should be tracked. Should cycle be tracked or be recorded, I guess is consistent with the words we used before. Should cycle be recorded? You give me a cycle, I will tell you yes or no. should it be recorded? So this isn't changing how our logic works. This is just rewriting the code so that it's a little bit easier to understand. And so the way that we determine if it should be recorded is we just say, hey, is it one of these? So if it's a member of that list, great. That means that we want to jot down what it was. So we just keep around the ones that we want to record. So then we can say pair this with before.register x. So pair this with is just a function that takes in a register value, and it takes in a cycle, and it just kind of puts them together in a single value. And the reason that we do this is because we want to use dict from list, and dict from list is going to expect a key value pair for each item in the list. So this is going to be the value, this is going to be the key, this is going to be the key value. You could also call this cycle to be a little bit more consistent with what we might expect. Register value. So when we start, we have a list of cycles. When we call pair this with, what we're doing is we're transforming each cycle into one of these. So we end up with a list of cycles and register values, only the ones that we cared about recording, because this step filtered it. And then we're going to have dict from list is going to convert this so that the first item is the key and the second item is the value. And then when we union these dictionaries together, we basically just combine it with what we had so far. So if I compile this, we're still looking good. What we want to do is we want to run this on that bigger example. So I'm going to save this real quick just in case something crazy happens. And what we're going to do is we're going to run this larger program. And we're going to see if we get the values that we expect in our history. So I'm going to replace this puzzle input with this huge program. And so what we see is our history is successfully recording things at all these values. So up top, let's do the exact same thing where we kind of comment what we've got. Puzzle input is a string. String lines gives us a list of strings. When we filter map with toInstruction, what it does is it converts all those strings to instructions and just uses the maybe to drop invalid input. So we don't have to worry about unsafe user input here. And then list.foldl is going to loop through and give us a model. So now that we have a model, the way to get the history out of it is just to call .history. So we can use .history function. This will give us a dictionary of cycles and register values. Just to show you that that's only grabbing our dictionary, this is what we have here. What we're going to do is we're going to turn this back into a list. So just like from list took a dictionary, or it took a list and turned it into a dictionary, we've got another function called toList, which does the exact opposite. It'll take this dictionary, turn it into a list, and what's great about this list is we can do list.map, and we can grab the cycle value, we can grab the register value, and we can multiply those together. So before I do that, let me just show you, we've got a list now. I'm gonna uncomment this out. If we take the cycle and we multiply it by the register, hopefully we're gonna see a list of numbers that match the numbers that we saw in our example puzzle. So 420, 1140, 1800, you got 420, 1140, 1800, then we've got 2940, 2880, 3960. 2940, 2880, 3960, and then it wants us to sum all those numbers up. That's going to be really easy. So this is a list of ints. It's going to be really easy because comes with a list.sum function that just adds up all the numbers for you. So 13140 is the answer to this puzzle. So what I'm going to do is I am going to save this program. It's going to be saved as day 10 part 2. I'm going to copy this for the video description below so you can run this yourself. And then I'm going to try it with my puzzle input. So now that I have my puzzle input, I'm going to copy all that. Your puzzle input's going to be different than mine, so your answer is going to be different. But if you go to Advent of Code, you can get your own input, and hopefully this program will work the same for you. And for my puzzle input, it looks like 13,820 is the answer. And that's right, you get 1 gold star, so that's awesome. So that was part 1. We're doing pretty good. Part 2 is going to add some twist to the puzzle. Hopefully our code is flexible enough, and I've read the instructions carefully enough this time that it's not going to take us too long to add this. So fingers crossed. Let's dive in and see what part 2 is about. All right, part 2. It seems like the X register controls the horizontal position of a sprite. Specifically, the sprite is 3 pixels wide, and the X register sets the horizontal position of the middle of that sprite. In this system, there is no such thing as a vertical position. If the sprite's horizontal position puts its pixels where the CRT is currently drawing, then those pixels will be drawn. You count the pixels on the CRT. It's 40 wide and 6 high. This CRT screen draws the top row of pixels left to right, then the row below that, and so on. The leftmost pixel in each row is in position 0, and the rightmost pixel in each row is position 39. Like the CPU, the CRT is tied closely to the clock circuit. If a CRT draws a single pixel during each cycle, representing each pixel of the screen as a hash. Here are the cycles during which the first and last pixels are drawn. So cycle 1 all the way to cycle 40, 41 all the way to 80, etc. So by carefully timing the CPU instructions and the CRT drawing operations, you should be able to determine whether the sprite is visible and the instant each pixel is drawn. If the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn, the screen produces a lit pixel, hash. Otherwise, the screen leaves a dark pixel, dark. So, interesting. If the sprite is positioned such that one of its 3 pixels is the pixel currently being drawn, the screen produces it. All right, first few pixels from larger example above are drawn as follows. Start cycle 1, we begin executing add x15. CRT draws pixel in position 0. Current CRT row is hash. This is really confusing. CRT draws pixel in position 1. Oh, okay, this is building up the sprite position. Okay, so cycle 1 draws a pixel. Draws a pixel. Finishing. Begin executing add x minus 11. CRT draws a pixel in position 2. Sprite position. Oh, okay, the sprite position is 1 initially. Got it. So now it's 1, 2, and 3. Okay. Got it. So when CRT draws pixel in position 1. So that's during cycle 1, CRT draws a pixel at position 0 because the sprite position is 1, 2, and 3. When it draws at 0, it hits the sprite, which draws a hash. CRT draws pixel in position 1. Current CRT row is hash because the pixels hit. At the end of cycle 2, we finish executing add x15, and as soon as that happens, the sprite shifts over. Got it. So now it's shifted over to 15, 16, and 17. So when I go to draw the pixel in position 2, I get a dot. Finishes executing add x11, which moves this back over, and then cycle hits. This is wild. Okay. So it's going to keep going until it draws this. Render the image given by your program. What 8 capital letters appear on your CRT? Dang. Okay, so for each cycle of the program, 220 cycles, it's gonna write some letters out for us, and we're gonna type in those letters. That's cool. Okay, so let's start by undoing and going back to the. Let's go back to the puzzle input that we had. So I think this is the 1511. Okay, this is the one that gave us the other 13 number. Okay, 13140. Cool. So what we need to do is we need to draw at each pixel. So we're just gonna draw. So history was keeping track of the values at these pixels. What I think we want to do is instead of recording the register values, let me just do a bit of formatting here. I'm gonna hit Elm format, and it's gonna jumble up all my comments. I'm gonna just delete them because that's too bad. But what we want to do, I think we want to record the full history for each cycle, and if it hits the sprite or not. So we're gonna say history should cycle be recorded, rather than recording it at 20, 60, 100, and 140 and 180. This function is going to change, and it's going to depend on the register value and the current cycle. So I think now the register value is going to become an important bit of input here. So this isn't going to determine if we're supposed to be recording a cycle. We're going to record a cycle if sprite, which is a list of cycles, which is list.range of whatever our register value is, plus, our register value all the way up to our register value plus 2. So if our register value is 1, this is going to be a list that's 1, 2, 3. If our register value is 15, this will be a list of 15, 16, 17. And then this is going to determine if we take the cycle and we mod it by 40, does it start drawing at 20 or? No, it starts drawing right away. We're going to get the wrapped cycle, which is just going to be a int. These ints are kind of going to be like columns. What we need to do is we take the cycle that we have. We're going to subtract 1 from it. Sounds kind of weird. But if it's 1, we're going to bring it down to 0 because we're going to want to use basics.remainder by 40. Then we're going to add 1 to it after we do that. So we're going to make sure that it's divisible by 40, and then we're just going to add back that 1 once we do that. And then what we're going to say is the wrap cycle a member of our sprite values? If it is, we should record that pixel. So this is more like should pixel be drawn. So should cycle be recorded? That's one way to do it. That's one thing to call it. We could call it should pixel be drawn. But the only difference is I need to know the value of the register. So I'm going to make sure the register comes first here. So now I'm recording a bunch of pixels. And so rather than doing all this work at the end where we're like printing out the sum, what I'm going to do is I'm going to loop through 1 through 40. and then I'm going to loop through 41 through 80. I'm going to keep doing that. And then for each of these, I'm going to draw a pixel. So let's just start by saying this is going to be our pixel map. It's going to, if you give me a cycle, I'm going to give you a, so I'm going to give you a register value at that time. I don't think it matters what the register value is. I don't think we have to record that part anymore. But what we want to do is we want to print out kind of like 2 lines. So in Elm, this is great because we can just actually write some HTML. So HTML pre, and then what we can do is we can say code, and I'm just going to show you a little example here. Hello. This is going to render some HTML out on the screen. And I think if we do multiple pre-blocks, what you'll see is that these render on top of each other. So I'm going to do a div, and then I'm going to just render a little bit of code that says line 2. I'll make this say line 1. Of course, our code's not going to be this noisy. We're gonna use some loops to do this. But what you'll see is that all of these are going to come together. And we can also just kind of print it all out in one go. But I think what I'm going to do is I'm going to say, I want to view the answer. View the answer. If you give me the pixel map, I can view the answer. So view answer takes the pixel map. That is this dictionary. And then we're going to return some HTML. So for each line, what I think we want to do is we want to say list.range 1 to 40. List.range of 41. I'm just going to type these out because I think it's a little bit easier to understand. Say 81 to 20. Just look at the puzzle. It had all the things on the side here. So 80, 120, 160, 200, 240. $60, 200, 240. So all these are just going to be whatever this number is, plus 1. We could have had a computer do this math for us, but here I am typing it. Okay, so we're going to take all these numbers, and we're just going to pipe this into a function that says view output, view line. So view line, oops, I'm going to copy this. So view line is going to be a little internal function here. The reason I keep it internal is because I want pixel map to be in scope. I don't want to pass it in everywhere. So view line is going to take in a list of numbers. So 1 through 40, maybe it's 41 through 80. And then what it's going to do is it's going to return me some HTML. You linked. So what we want to do is if I can find that number in my dictionary, then I'm going to convert it to a hash. And if I can't, then I'm going to convert it to a, sorry, so these are our, I guess, numbers. So I'll take each number, list.map. If I can find that number, so if dict.member, the number I'm looking at, 1, 2, 3, 4, 5, all the way up to 40. If I find that number in my pixel map, then I want to turn that to this character, this hash character. Otherwise, I'm going to turn it to a dot. And then I'm going to do a string.fromList to take that list of characters, combine it into one string. And then what's cool about that is I can do my HTML pre-tag that we saw before. So we have the pre, the HTML code, and then we're going to have HTML text. And that is just going to have the output of this value. So this whole thing is going to be like the string that we want to print, or like the line that we want to print here. So say line as a string. That's just going to be our numbers one at a time. String list. Let's see how this goes. Okay, and here you go. So now we've got this printing out. It looks like we nailed it. It looks like this this looks right. I'm gonna kind of scrunch up the numbers. I think there's some inherent like spacing going on between these items. See if HTML editor went. Oh, there it is. So I'm just gonna get rid of the margin on our pre-tags here. So that'll make it nice and tight and hopefully easy to read what we've got. So I think this is part 2. Let me make this big again. And I'm gonna zoom this in so you can see. Hopefully that's a good size. I'm gonna take this, I'm gonna rename this to part 2. I'm gonna save, copy this. So we were recording a pixel each time that our sprite was hit. It looks like that did it. So what I'm gonna do now is I'm gonna take in my puzzle input. I'm gonna go back into the puzzle. Just gonna paste it in. And it looks like I've got ZKG. I'm gonna make the line height really small so we can actually like see it really nice. So we're gonna make the line height we're gonna make it really tiny. There you go. So hopefully you can see that a little bit better. I'm gonna add some letter spacing. Well, it doesn't really matter. I'll relax. But this is it. So I've got ZKGR KGRK. So we're gonna type that in wrong. I already forgot it. KGR KGRK. Two gold stars. Can you imagine if we got it wrong and it just happened to write these letters, this like perfect like ASCII art for letters, without it being correct? Yeah, that's the puzzle. I'm gonna just format this so we can kind of see what we did. Yeah, we didn't even have to use the register value here. That was just kind of left over. But I think, oops. There's like, oops. Kind of wonder if there's like a rectangle or something that we can render here to make it super visible. I'm just having fun at this point. But all the links to the source code are going to be at the bottom of this video. And I'm just going to scroll through. These are just Latin symbols, geometric symbols, math symbols, supplemental symbols, language symbols. No, this isn't it. I wanted a box. I wanted a big, full square. I'm gonna look up Unicode block. Ugh. There we go. That's what I want. Google did me good. So there you go. That's a little bit easier to see. And then we can just do a single character here. So that's what we got. Pretty cool. Awesome. Well, thanks for hanging out. That was day 10. It was a lot easier than day 9. There was a lot going on, but I had fun with this one. It was cool that it printed a message at the end. And that's it for me. I will catch you guys later. Have a wonderful week and happy having a code.